Good afternoon, good evening, good morning, everyone. Thank you so much for joining me today. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging, and I'm pleased to welcome you to this special ESTRO, I should say, webinar. Hope all of you who are attending that virtual ESTRO are enjoying some of those talks, and hope the rest of the week goes well for you there as well. I just want to stop, I guess, before I get too far into the small field topic and just say thank you to all of you who are working in clinics, who are doing your part to treat cancer. We know that cancer doesn't wait on a global pandemic. It marches on, and we need to do that, give the care that our patients need. We thank you for all of your time and effort in that as well. Just a little bit of housekeeping. We are recording the webinar today. If you walked in late, if you have to leave early because you're trying to get to another talk, I'll try and keep this to the half-hour break time. Or if I start talking a little too fast, you will get a link to a recording. You can go back and rewatch or listen to a part that you missed or would like to share with a colleague. If you have questions throughout my presentation, please feel free to enter them in the GoToMeeting dialog box. I'll try and answer those as I go along. And for those of you who aren't so familiar with Standard Imaging, we are based in Middleton, Wisconsin in the United States. That's just outside the capital city, or Wisconsin state capital city of Madison. We were founded in 1989 and started from some humble beginnings with just a few products and have grown to the point now where we design and manufacture a full suite of QA products for radiation therapy. And we invite you to become more familiar with us if you haven't heard of us so much in the past. So to the topic at hand, what makes small fields so very challenging? And it seems intuitive to say, but really size is the first problem that you encounter, just the sheer small size of these fields. There are a few other things that affect your measurement: source occlusion, changes in the energy of the field as the field size decreases, changes in the shape of the penumbra of the field, of course, loss of lateral charged particle equilibrium. And I'll touch on a bunch of these in a little more detail here, but just to point you to some very excellent references if you need something to help you understand some of these concepts better. Obviously, I'm not the ultimate authority on it, but a lot of the information that I'll be presenting I pulled from the IPEM report on small field megavoltage photon dosimetry and the joint report from the IAEA and the AAPM TRS 483. So what is a small field? What are the conditions required? TRS 483 defines small fields as having at least one of these three conditions: either loss of the lateral CPE on the beam axis, some occlusion of the primary photon source by the collimating devices, again on the beam axis, or the size of the detector is similar to or large compared to the beam dimensions. So the first part, physical size. Generally, small fields are between 4 and 40 millimeters. The field size definition is a little bit more tricky because usually you would use the JAWS settings or collimator settings as you're looking at decrease or at those field sizes. But with small fields, it may actually behoove you to look more at the full width half max, just because if this graphic kind of illustrates the jaw position in blue, but the full width half max tends to spread out as those jaws decrease just because of the way the penumbra is shaped by each of the jaws. You also get, as we know, a decreased output. This peak decreases as the field size goes down. And with that physical size, alignment of your detector becomes a much more critical issue. A small misalignment of the detector can mean a very large geometric or dosimetric error or miss. The next issue is source occlusion. So as you're looking at a larger field, the measurement point sees the primary beam from the entire target, whereas with a smaller field, part of that target gets blocked. And so actually part of the primary field gets blocked at your point of measurement. Lateral, I can't talk today. Lateral electronic equilibrium is referring to a condition in which the lateral scattering distance is equal to or greater than the range of electrons. And if I translate that into a little bit more practical language, you'll likely start losing your lateral equilibrium when your beam width is less than twice your Dmax. So in this plot, the higher energies are the ones down here. They lose their plateau sooner with a larger beam radius than the lower energies do. Because of that range of those secondary electrons. So your detector positioning, your perturbation corrections come into play a little bit sooner for the higher energy beams as you're going down in field size. This also is a good reminder that it's important to characterize not just your output factors, but also your beam profiles. So how do detectors impact your measurement? Well, first and foremost, your detector size and shape are going to impact the measurement because of the volume averaging that occurs. So it's good to know what your field profile is compared to your detector spot size. You also want to know if you have a detector that is uniform in both directions in terms of its collecting volume, or if it's stretched out in one direction, because the orientation then will definitely affect your volume averaging. It's not just a question of how small your chamber is, but what shape is it as well. You also, obviously, with your detector need consistent and accurate positioning in order to get repeatable measurements, especially in these small fields. Second way that the detectors impact your measurement is by perturbing the beam right there at the point of measurement. So when you put something in the field that is not water equivalent, you're altering the dose that's deposited, you're altering the interactions of the radiation by replacing water with your detector. So things to ask when you're figuring out what to use for these measurements, or making measurements for an ion chamber, you want to know how big your air cavity is, obviously what the shape is, as we just talked about. For a diode, what's the density of the diode? How does that perturb the beam? Does your diode have built-in compensation? This is usually an air gap to try and balance out the higher density of the diode itself. And so those are often good for the energy range in which they were designed, but then they can have other complications, responses varying with other energies. So be aware if you have a compensated diode, where it needs correction and where it doesn't. There are published corrections sometimes available for detectors, but the thing to be careful of is that a lot of these correction factors very much depend upon the energies and the setup that's used. So if you're going to use those published corrections, you need to make sure that you're matching the published conditions as well. Third way the detectors are impacting your measurement is the signal. So for your ion chamber, your signal is proportional to the collecting volume. The more air volume you have, the more ionization occurs, the bigger your signal. So as you're going down to these very small chambers for small field measurements, your signal to noise ratio becomes much more of a concern. And with small signals, you need to make sure you have an appropriately sensitive electrometer that you've characterized properly. For a diode, you do get a larger signal than from microionization chambers, so signal is not as big an issue and SNR is not as big an issue for diodes. Be aware of your signal to noise ratio. You need to make sure that you've given your electrometer a proper warm-up, you've checked for leakage. You need to make sure you've matched your signal strength from your detector to your proper electrometer range and have zeroed that range first. And then one that was kind of a surprise to me when I learned it recently from one of our electrical engineers is that, well, I knew about some triaxial cable effects, so you have some stem effect potentially from chamber extension cables, but there are sometimes triboelectric effects from a cable that's just been unwound. So if you've just laid out a big long cable from a tight spool in through the raceway into the vault, it can take a few hours for that chamber to settle. So if your system doesn't hold at zero, check your cables first. Think about how recently you unwound them. check your zero and your leakage without the cable attached. It may be that your cable needs to sit for a little while, or it may be that you have an older damaged cable that's not functioning properly, or rather shielding your signal properly. There's also cable-induced signal, sometimes due to irradiation. If you're irradiating a large portion of your cable, you'll create some constant current in that cable. Accuracy of your detector. Does your detector have energy dependence? Diodes sometimes have a low response out of the field and will underestimate that large region of low dose in stereotactic patients. We talked about compensated diodes that could be good or could be bad depending on the diode itself and the measurement conditions that you want to use it in. Corrections may be depth dependent if you have energy dependence for your detector because of the energy changes as the beam is attenuated by the material. Obviously, changes in scatter conditions may affect your response because of the variation in energy just due to the scatter as well. Accuracy of the detector is also impacted by your angular dependence. The best thing to do, especially in characterizing your small fields, is to make sure that you're using your detector in the orientation for which it was designed. Otherwise, you need to be aware of the implications of changing that and correct for it appropriately. A lot of detectors also have dose rate or dose per pulse dependence, which means that you need to understand both your accelerator and your detector. Some accelerators do change the size of the pulse. A lot of them do or change the frequency of the pulses when you change the dose rate. So that's something that you would need to be aware of and be able to correct for if needed, etc. There are a few other things that I haven't gone into in great deal here. There are a lot of other types of detectors, gels, film, OSLDs that can be used. Things to think about: how accurate are they? Do they have leakage or drift? How long does it take for GAF chromic film to settle? How repeatable are your measurements? What's the resolution of it? Can it be calibrated? Those sorts of questions. So what's a poor physicist to do? Sometimes it looks like a puzzle, a black box, trying to figure it out. Sometimes it feels a little bit more like a ticking time bomb. You're handed a project that we are going to start a stereotactic program. I need you to calibrate these cones, and waiting to figure out a solution is potentially asking for disaster. So we need a solution now, obviously. So options for megavoltage beams. I have 3 to offer you today. One is established technology with some known perturbation issues in the diodes that we offer. One would be new technology in the scintillation detectors that we have. And one is an old standard, the ionization chamber, finally working properly in miniature form. So let me talk to you about A26 as well. So all of these detectors have both strengths and limitations, just like every detector that's out there. The best solution for your small fields is really going to be a good combination of complementary detectors. So with our diodes, the D1V and the D1H, it's the same diode, just different housing. The D1H for horizontal is really designed for use in solid phantoms, slab phantoms. The D1V is used for scanning. They're unshielded diodes with a 1 millimeter diameter spot size, and there are correction factors published. There were in particular 2 publications in 2014 that looked at both measured and Monte Carlo calculated correction factors. Strengths of the diodes: really, diodes are well-established technology. We're comfortable using them as physicists. We can use them for scanning. They have minimal volume averaging with the small measurement area, small spot size. And these diodes in particular have fairly low angular dependence, although they do have some, as every diode does. Limitations of these diodes: of course, they're diodes, they're not water equivalent, so they do require some corrections as your field size changes or your energy changes, and there is a little bit of angular dependence, as I mentioned. The second option I have for is a newer technology, I guess. So we've had some of this on the market for a little while here. It's an organic scintillating material available either as a 1 by 1 millimeter or a 1 by 3, but it's completely water equivalent for megavoltage photons and electrons, which is really helpful in these small fields. The one thing it does require is a Cherenkov correction for the stem effect. Cherenkov light is produced in the optical transfer fiber. And it does require a reference dose. So you have to give it a periodic recalibration, both for the Cherenkov light ratio, that's what CLR stands for in the bullet point there, and for accumulated dose as the material accumulates or is given dose. It's a plastic fiber, as we've, I think, all seen with some clear plastic phantoms, they do tend to yellow with age. And that discoloration of the fiber is what affects the transfer of the colors. And since we correct for Cherenkov, using a two-color chromatic correction, the spectrum that's transmitted down the fiber does matter. So for the W1 scintillator, which was our first generation scintillator, is a 1 millimeter diameter, 3 millimeter long active scintillation region. And that TRS 483 publication from the IAEA on small field dosimetry does have correction factors, field output correction factors for the W1. And in every table that it shows up in, the correction factors are unity all across the table. And that's an indication of the water equivalence of this detector. And we're quite excited to have that that data published. Just to be aware, where this document does not publish values, that indicates that the stability and the uncertainty of the detector was unsuitable for field sizes that small. Strengths of the W1 is first and foremost, of course, that beam quality correction factor is 1. It simplifies your small field measurements so much not to have to be applying those corrections on top of all the corrections that you normally do for your TG or your calibrations, or even output factor measurements. They are water equivalent for megavoltage photons and electrons, which of course is reflected in that beam quality correction factor as well. We have not seen dose rate or energy dependence with this detector. It has a negligible temperature dependence, so if you're using it just at room temperature, you don't have to correct for the temperature. It's about 0.1% per degree Celsius. Limitations of the W1, really it was not designed for scanning or for large fields. This was designed just as a single point measurement detector. It does have a pretty low signal to noise ratio, so there is a higher uncertainty if you were trying to measure some out of field doses or low dose region. As we mentioned, it requires a reference dose. It's not an absolute absolute detector. Dosimeter, that's the word I wanted. It's not an absolute dosimeter. It needs to be given a known dose in order to convert the current readings that we get from the light that's generated into dose, and you do occasionally need to recalibrate it. One of the other limitations that we've found with users of this device is that optical signal measurements really are non-intuitive to many users. We're used to ion chambers. We're very comfortable with ion chambers. We're used to diodes. We're not so used to troubleshooting issues with optical measurements. And so it does take a little bit more work at the beginning when you're just getting comfortable with how to use it. The W2 is our second generation device. It's been out for a couple of years now, year and a half. We improved the optics on this detector so that we could go down to a 1 by 1 millimeter fiber. We also kept an option for a 1 by 3 millimeter. They're interchangeable fibers, so actually if you get the kit, you get both. So that you can have the fine resolution when you need it, but you can also have a stronger signal, lower SNR, or higher SNR, sorry, and that direct comparison with the W1 because the fibers are the same with the 1 by 3. It has dedicated electronics. The W1 did need the 2-channel electrometer, like our Supermax electrometer, which has a built-in feature to work with that scintillation detector and to apply the Cherenkov corrections. We have a dedicated electrometer with the W2 called the Max SD that combines the optics and the signal processing electronics. In order to decrease the electronic noise, that was the other reason we could go down to a smaller detector. You can perform point dose measurements directly with the Max SD, but it will also do a fast Cherenkov correction every 10 millisecond integration and convert the Cherenkov corrected signal into an analog output that can be sent to a water tank scanning electrometer. So you can scan directly with this, or you can scan with this W2 using the interface of your water tank. Oh, that's not what I wanted. So strengths of the W2, we've managed to keep, of course, all the strengths of the W1 because it is the same fiber, and we took away a couple of the limitations so that it can be used in a little bit more versatile manner. And the final option that I'm happy to put before you here is the microionization chamber called the X-Radon A26. This has been on the market for a few years now, but it was designed as a result of Jessica Miller's PhD thesis investigation at the UW-Madison into the behavior of all of the microionization chambers that were on the market at the time. And it wasn't just standard imaging ionization chambers, it was everybody's ionization chambers. And the particular issue that people were having or noticing primarily related to polarity and some I don't want to say non-realistic, but non-intuitive behavior, very strange behavior sometimes with the change in polarity. And this was traced to some of the construction of the chamber. And with the findings from her thesis, we were able to create a very small conductive plastic ionization chamber that had very stable polarity response, stable ion recombination, and so it behaves just as a reference class chamber would, except it's very small. So it was designed to provide that reference class measurement for your small fields. Strengths of the the A26 is really it is a reference class ionization chamber. It has a circular spot size, so the spot size is independent of the orientation of the chamber, which is very helpful for your volume averaging corrections as well. And it's a very small spot size. It's also a familiar technology for most physicists. We're used to using ion chambers. Limitations are really, it does require corrections to account for the air volume. It's an ionization chamber, and you're stuck with some of those limitations. So I'm about done. I know the break is just about over. Hopefully I'm not running too late. I forgot to check the time. We're good. I'd be remiss if I didn't bring up some electrometers. If you're trying to do small field measurements, you need a good, reliable, accurate, stable electrometer. So our two primary electrometers are the Max 4000 Plus, which seriously is a workhorse. So these things just keep on going. They're wonderful. So it's a very robust single channel reference class electrometer. The Supermax is our high-end electrometer. It is that dual channel with independent bias, has a very short warm-up time, and of course could be used with the W1 scintillator. Both of these electrometers have an industry-leading 5-year warranty. We're good at making electrometers, and we're happy to stand behind them. You can count on these electrometers working for a long time. So together, we can conquer the challenge of small field dosimetry. We'll help you through it. Please feel free to reach out with questions. If you go to standardimaging.com/welcome, that's our Eastro page. Look for the webinars listed there. Feel free to reach out to us directly to sales@standardimaging.com if you have questions, or directly to me, sholmes@standardimaging.com, if you have any questions that you don't get answered here, or would like some follow-up information on any of this. So with that, I will conclude, but if you have any questions, please feel free to enter them in the GoToMeeting dialogue now. I will stick around and answer some questions if there are any. Otherwise, please enjoy the rest of your day, enjoy the rest of the Eastro conference, and join us again sometime in the future. Thank you.